It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sandra Houston. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Unsaturated Soils was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on assessment of stress path strategies for applied unsaturated soil mechanics using the modified state surface approach was delivered by Emeritus Professor Sandra Houston at this workshop. Sandra Houston is Emeritus Professor in the School of Sustainable Engineering and the Built Environment at Arizona State University. Professor Houston's contributions to the field of geotechnical engineering focus on unsaturated soils and arid region problem soils, including in particular collapsible and expansive soils and unsaturated flow. Sandra has served in numerous leadership positions in the American Society of Civil Engineers, Geo Institute, and the International Society of Soil Mechanics and Geotechnical Engineering. She is a recipient of the 2017 ASCE Terzaghi Award and the 2004 William H. Wisely American Society of Civil Engineers Award, past president of the Geo Institute, and past chair of the ASCE Board Level Committee on Diversity and Inclusion. She served as the formational chair of the GI Committee on Unsaturated Soils, and served many years as a U.S. representative and secretary of the TC 106 Committee on Unsaturated Soils. Sandra was awarded the first Distinguished Lecturer for the Pan American Unsaturated Soils Conference Series by the TC 106 Unsaturated Soils Committee.
I appreciate all the work that you've done in getting this conference together. Today, what I'm going to do is I'm going to talk about complex unsaturated soil behavior and how we take that complex behavior to simplified solutions. And in particular, we're going to look at the role of stress path and the modified state surface approaches in evaluating our simplified solutions. So just as a reminder, the unsaturated soil volume and change and shear strength is controlled by two independent stress state variables. Those are the mean net confining stress, P or sigma minus UA, and the matrix suction, S or UA minus UW. Now it's important to note that we select these two variables because the net stress and the matrix suction are measurable. They're both controllable external to the soil, and both have been demonstrated in the laboratory to be effective in controlling both shear strength and volume change response. The matrix suction in particular is of interest. It's associated with the soil moisture state, and it is applied and controlled externally, for example, by climate, irrigation, plants, groundwater table position, and so forth. But because the matrix suction is related to the moisture content, the water content takes on a particular importance due to its relationship to the soil state of stress when we're dealing with unsaturated soils. So in dealing with the practice of unsaturated soil mechanics, the most important thing to keep in mind is that you have to keep your eye on both the net stress and also on the suction variables as you proceed with your solutions. This shows you a sample SWCC that shows that the water content, here is the volumetric, is a function of the soil suction. And this happens to be a drying zero confinement SWCC that I've shown you here. And again, going into the practice, the independent roles of the net stress and total suction, the independent roles of the net total stress and suction are important even at this point when you're doing the site investigation. So for example, when we select the depth of sampling and testing, normally what we are doing is we are looking at the depth of exploration and sampling on the basis of looking at stress bulbs, such as the ones that I've shown here, which is effectively like looking at the net total stress alone. However, when we have unsaturated soil mechanics, we also need to think about the depth of wetting. And so here we have to think about what is the natural state of moisture in the soil, what will be the conditions after construction, and what is the difference. So we need to look at the natural state compared to the post-construction state. And what we find is that very frequently the depth of influence of the net total stress may be much less than the depth of wetting or the depth over which we have changes in the suction. So we have to couple these two things together then in order to figure out what our depth of sampling and testing is going to be. Okay, if we look at the common tests that are performed in practice, certain tests can be assumed to be kind of comfortable from a routine practice perspective. So for example, very commonly performed in geotechnical practice are the 1D odometer test. For example, the response to wetting test, the ASTM D4546, saturated triaxial test are fairly common, saturated direct shear test, saturated hydraulic conductivity test, and then of course a host of indexed gradation tests. So these are things that we can assume are not too much to ask for a practicing engineer to perform. And more recently, what has become somewhat common in geotechnical practice is to either measure or estimate soil suction, and certainly measurement of soil water characteristic curves can be assumed. So the question arises, how are we going to use these common laboratory tests in developing procedures for dealing with certain problems in unsaturated soil mechanics practice? So let's first take a look at how do we use these common tests for unsaturated flow problems, or some might call them seepage problems. Now, in general, the unsaturated hydraulic conductivity function can be relatively simply estimated by first looking at the saturated hydraulic conductivity and then measuring the SWCC and empirically combining those together to get an estimate of the unsaturated soil conductivity function. So over here, I've just shown you one example that is fairly common, which is the Van Newton-Wallem model. And so it is based on the saturated conductivity and also the SWCC relationship empirically, as the equations show here. I would also note that in general, when we're making this relationship between saturated conductivity and the unsaturated conductivity, it's fairly typical that we will not take into account the volume change in making that assessment. So once we have the unsaturated hydraulic conductivity function, we're now going to use this in an unsaturated flow analysis. So the unsaturated flow analyses, there are many computer codes available for doing such an analysis. And in spite of the fact that we have some challenges in modeling relatively complex surface flux conditions, these unsaturated flow models have proven very useful in practice for looking at various what-if scenarios. What if we get a ponding, or what if we plant a tree, or we remove a tree? Also, probabilistic-based analyses have proven very useful in practice in dealing with unsaturated flow problems. An alternative to doing an unsaturated flow analysis would be to use something like a field database for particular field conditions. And so this has been empirically developed for certain limited cases. For example, we have looked at a lot of field suction profile databases for expansive soils. And there are empirical models that have been presented by Litton colleagues. In particular, we see those a lot in the post-tensioning institute methods that are widely used and published, and also in some recent studies by myself and Van. And so over here, in fact, what you'll see in this sketch is a plot of suction versus depth. These happen to be normalized for climatic change conditions. And the climate, the various climates will affect the shape that we get. And the climate is judged on the basis of TMI, which is the Thornthwaite Moisture Index. These do have some benefits in that these empirical models are benchmarked to field data and they're pretty easy to use. But the con is that they have limited application. Here, for example, we're only looking at climatic change and we're only looking at expansive soils where there's relatively deep groundwater table. And also the data sets that we use, because they're field data, will often have some significant amount of scatter, which we have to deal with in our uncertainty. Now, if we take a look at these models, these unsaturated hydraulic conductivity models that we get by using the saturated conductivity and then empirically adjusting on the base of the SWCC, what we will find is that there's some relatively complex and highly nonlinear results that we get. So if we look at the hydraulic conductivity or coefficient of permeability as a function of matrix suction, if we look at the result for a fine sand, of course, when we have low suction, such as 0 here, we know that the sand is going to have a higher hydraulic conductivity than the clay, and in fact, maybe several orders of magnitude. But what we know is that as we increase the suction, that our unsaturated hydraulic conductivity is going to begin to decrease. And at a certain point, in fact, we get a crossover where when the suction gets high enough, we actually have the clay with a higher hydraulic conductivity than the sand. So this makes intuiting what's going to happen in the field somewhat challenging. And we need to keep this in mind when we're doing unsaturated flow analyses. The unsaturated clay can carry more water than unsaturated sand or gravel, for example. If we're not aware of this, then we can make errors. For example, you may find that your gravel drains will not work under unsaturated flow conditions. Or conversely, we can actually use this knowledge to enhance our designs, and dealing with these complexities can actually lead to solutions. For example, the evapotranspirative landfill covers is a very good example. And I know that Professor Raharjo has talked to you about some of his very fascinating work along these lines. So we've kind of developed a pretty good protocol for dealing with practice-based unsaturated flow problems. And it kind of generally goes like this: obtain the saturated soil hydraulic conductivity and measure the SWCC. Then 2, use empirical correlations to obtain unsaturated soil hydraulic conductivity at various levels of suction. And then use these estimates of unsaturated conductivity in the SWCC in unsaturated flow, various what-if scenarios. So been done for a long time. We're doing a lot more interesting applications, but the protocols are relatively straightforward. Similarly, if we look at how do we use common laboratory tests in dealing with practice-based shear strength problems, what we find is that shear strength has been studied quite a bit, and we find that the shear strength of unsaturated soils is usually going to increase with matrix suction. So if we take a look here at the plastic clay curve, you'll see that as the matrix suction increases, we get an increase in shear strength. Similarly for silty soils, and eventually it kind of levels off. Really the only exception that we have is with cohesionless sands, non-plastic materials, where when they get dry enough, their shear strength is going to fall off. And also when they get too wet, their shear strength is going to be somewhat different than their peak. It's going to be very low. Classic example of this is the sandcastle. If the sand is too dry, you can't build anything, or if it's too wet, you can't build anything. But setting aside the non-plastic soils, the general response is that the shear strength of unsaturated soils will increase with increasing matrix suction, which means as the soil dries, it's going to get stiffer and stronger. So there are a lot of empirical relationships that exist for estimating unsaturated soil shear strength. I've put up here a couple of them that you're probably familiar with because they've been around for perhaps some of the longest period of time. And essentially the way that it is let's take a look at the Kalili down here. The shear strength is calculated from the saturated soil cohesion intercept C prime and the friction angle phi prime for saturated conditions. And so we have the C prime sigma tan phi plus a component that is related to the soil suction. Okay, so the shear strength typically increases with increasing suction when we deal with practice-based problems. It makes it possible that we can utilize empirical chi-type single stress formulations, such as the ones that I've shown here, for many limit equilibrium practice-based applications. For most applications, it's acceptable to use these empirical relationships, but note that these empirical relationships ignores the exceptions, such as the one that I showed with the clean non-plastic sands, where the shear strength can drop off as suction is increased. But barring these exceptions, and for many, many applications, we can use these, and you'll see that these have been used, in fact, in looking at slope stability problems, retaining wall problems, bearing capacity problems. So we have a fairly well-established common protocol for practice-based shear strength problems. One, obtain the saturated soil shear strength parameters, C prime, phi prime, measure the SWCC. 2, use empirical correlations to obtain unsaturated soil shear strength at various suction values. And then 3, estimate soil suction values and use the estimated unsaturated soil shear strength in limit equilibrium analyses. So fairly simple 3-step protocol, similar to the one that we used for the unsaturated flow. We get the saturated properties, the SWCC, develop empirical correlations, and then proceed with the analysis. Okay, now let's take a look at volume change. How do we best use these common laboratory tests when we're dealing with unsaturated soil volume change response? Well, as I mentioned, a common protocol for practice is to first measure saturated, then estimate the unsaturated soil properties response using empirical methods, typically based on the SWCC. However, when it comes to volume change, this cannot work well. And so what we find is that volume change is the most complex, and I would say arguably the most important unsaturated soils application. It's been known for a long time that volume change needs a different protocol than shear strength, for example, and from unsaturated flow. Fredlin and Houston in 2009 conclude in their paper that a hierarchical level of approach to unsaturated soil property assessment is desirable, taking into account situation-appropriate level of testing and analysis. For example, a different level depending upon the level of risk, or whether you're doing a preliminary design or a final design. However, separate protocols for routine practice are required for shear strength problems, fluid flow problems, and volume change problems. Okay, so what makes volume change such a different thing, and why is it so different in development of protocols? Well, as we have learned, it's difficult sometimes to even intuit the direction of volume change. Is it going to be expansion or compression when the soil becomes wetted under load, unless you have laboratory test results? What we're looking at here is a depiction of the volume change in response to full wetting, that is full wetting to suction equals 0, of a particular clay soil. And this clay soil has been compacted at a low density, a medium density, and a high density. Let's just take a look first here at the medium density curve. If I happen to run a response to wetting test in an odometer device by first applying a stress level that is relatively low, such as at this point, and then I wet it fully, I'll probably expect to get a swell strain response. And in fact, I commonly do. But if instead what I do is I load the specimen to a much higher confining stress, such as this point here, now when I give the soil full access to water and let it wet completely, I will get a compressive or a collapse response. And so how much of response, of course, depends on the density, but this is a very common type of scenario for any soil that has some plasticity. So this, looking at it in the 2 stress state variable perspective now, this behavior presents itself as that warped state surface that Professor Zong presented to you earlier, and that was first presented by Mathias and Radhakrishna in 1968. So this is a plot of our void ratio versus suction in one plane and the net normal stress. And what we can see is that if we start here at point A at some value of suction and a confining stress level P that is relatively low, when I decrease the suction, I will get expansion, A to A prime. On the other hand, if I start here at a high stress level and I wet the specimen, then what I will see is that as I decrease the suction, I can actually get a collapse or a compression response. And so this gives us the warping of that state surface that we have to deal with. So the unsaturated soil volume change is nonlinear. And the other thing that we know is that the unsaturated soil volume change response is elastoplastic and stress path dependent. We see this very clearly in the modified state surface approach that we learned about in the previous lecture. So what you see over here is a depiction of the elastoplastic unsaturated soil response to changes in net stress and changes in suction. We have a unique virgin loading surface as depicted here. And then we have a downward movement of the elastic surface as yield occurs. So for example, what we get is some path dependency. If we start here at D in the elastic surface and we load to E, we can unload back elastic and come back to E. But if we increase at constant suction by increasing P, we will end up here, say, for example, at point V. Now, if we unload, we're going to unload along an elastic surface, which is now lower. So our first elastic surface was AGHB, but now that we load to V, our new elastic surface is A prime, G prime, U, and W. And so when we load from V to, for example, unload completely to 0P, we'll end up at a point D prime. The main point of this is that we have elastoplastic response and we have stress path dependency. It's very clear to see from the MSSA view. So the complexity of the unsaturated soil response is a lot like trying to analyze that is a lot like these blindfolded men trying to analyze this elephant. So each blindfolded man, in his own opinion, exceedingly stiff and strong, though each was partly in the right and all were in the wrong. So for example, if you're looking only at the ear, you may think that this is a fan. Or if you're looking at the tusk, oh no, it's a sphere. At the tail, it's a rope. Or the leg, it's a tree, and so on. And so if you look at only a piece of the picture, you can get a very wrong view of what things actually are. So analogously, a fundamentally sound unsaturated soils theory must hold a holistic view of the unsaturated soil volume change response. And this is particularly true given the complexity of response that we have to deal with. Conversely, using an incremental approach, for example, analogous to using incremental plasticity, perhaps writing equation only for the wall, an incremental approach may result in part of the model being correct, but not applicable to other parts of the problem. So I'm going to just postulate to you here that we have the equivalent of an unsaturated soil elephant that is highly complex, nonlinear, elastoplastic, and path dependent. And the MSSA that we talked about in the previous lecture provides a much needed guide for evaluation of volume change models and also in the development of practice-based protocols. So we need to ensure that our simplified models are going to fit appropriately within the big framework. The MSSA, it's a new framework for constitutive modeling. It extends the state surface approach that was presented by Fredlin and Harjo in '93 into the elastoplasticity realm. Recognizes the complexity of the soil response, and here we're talking about volume change response, avoids traditional incremental approaches, which are fraught with challenges due to this complex behavior, and ensures compatibility between the model and the response by matching observed behavior. Also, as we know now from the previous lecture, the MSSA can accommodate both expansion or collapse, and therefore the same model can be used for both. Okay, so we already know that the elastoplastic models, such as the BBM and even the MSSA, are relatively difficult to use on a routine and for low-cost types of foundation systems and so forth. There are many long and expensive tests required, and the analyses can become rather cumbersome. So in practice, we don't always want to do that. But the question arises, how do we deal with such complex behavior in routine practice? So one, although the MSSA is very multifaceted, then you can't use the whole thing in routine practice. It does provide a sound framework for appropriate guide to evaluation of more simplified models and approaches. Also, the overall complexity, including the path dependency in particular of the soil response, points to the desirability of using a stress path-based approach. Now, this stress path-based approach is actually something that was presented in 1968 by Lamb, and we're going to use it here, the concept of it, for looking at unsaturated soil response as well, volume change response. If you're unfamiliar with the stress path paper and the approach, basically here it is. It recognizes that you have not highly nonlinear stress-strain response of soils to loading. The soil response and parameters are obtained from laboratory data that follows as closely as possible the stress path expected to occur in the field. And the response or the strains that you get in the lab are assumed to be the same as those corresponding to the point in the field, the reason being that you have matched the conditions and the stress path as closely as possible between lab and field. So this requires use of field representative specimens, so undisturbed specimens or compacted like your compaction specifications, closely matching both the initial stress state, and when it comes to unsaturated soils, we have to match the stress state in terms of both confining stress P and soil suction S, so that our initial state is matched. And thereby the complexities of the soil response are addressed through an approach of laboratory to field matching process. And that's the stress path approach in a nutshell. All right, I'm going to share with you an example of a simplified practice-based approach. It happens to be a odometer 1D K0 type volume change problem with monotonic wetting under constant load. The good news for us is that even though this is a relatively simple boundary condition that we're dealing with, it's applicable or at least relevant to many, many practice-based problems that we deal with in geotechnical engineering. The method is referred to as the surrogate path method, SPM, was first developed in the dissertation work of Sonal Singhal in 2010, one of my students at ASU. Was presented in the Pan Am conference by Houston 2018, and then in Houston and Zong 2021, we began to look at this particular method in terms of the MSSA. So the SPM remains as true as possible to the modified state surface framework of unsaturated soil elastoplastic response, but it limits itself to the use of routine odometer test results in the absence of suction measurement. And it takes advantage of the stress path type approach to solution. Okay, so the surrogate path method for estimation, it's estimating partial wetting, expansion, or collapse. It can be used for either expansion or collapse, and you do not have to assume full wetting. You can have wetting to suction values that are less than full wetting in the field, which in fact is the most common scenario. It uses simple and inexpensive testing requirements. The one that we use the most is the response to wetting odometer test with no suction control. And this is the ASTM D4546 method A or B and C, if you're familiar with that D4546 specification. You do this on each representative soil layer in the field. It does require, as all unsaturated soil analyses do, estimates or measurements of initial and estimates or measurements of final suction values in order to be used. So it basically what it is you take the stress path that is observed in the field, and then we're going to map that into the zero suction plane. So let me walk you through this just a little bit. We're going to assume that the D4546 method D test we're going to look at an expansion example here, and we're going to follow the path from I as the element of soil sits in the field at a particular value of suction and a particular value of confining stress. We start at I. So we have loaded our specimen to these conditions and matched the field. And then we're going to wet along path IF to B. And at B, this in fact is our swell potential for that specimen at overburden stress. So sigma OB is overburden. So the strain sub OB is the fully wetted strain or the swell potential that we get from the method B test. Now, the next thing that we're going to do is we're going to also either by load back using method C or a constant volume swell pressure test, we're going to get the swell pressure, which is depicted here as point G on the zero suction plane. And so that is where we can wet the specimen, gradually increase the stress so as to hold the void ratio equal to the value that it initially had in the field. So we have B, we have G from relatively routine test, and we're going to develop a path here on the, a path on the zero suction plane, which has a slope when it is presented in a log format of C sub SP, or the surrogate path slope, sometimes called C sub H, or the swell, swelling slope. So the mapping process is going to be such that if I map here at an intermediate suction value, say F, along the actual field path, the strain that I get in the field, epsilon sub F, is going to be matched exactly by the strain that I get at Q once I calculate my surrogate total stress sigma P. So here's how the computation goes. It's a relatively simple computation. The surrogate total stress sigma P at suction corresponding to F is the overburden stress plus a multiplier RW multiplied by the difference between the swell pressure minus the overburden stress. So sigma P now can be thought of as the surrogate final stress, and it corresponds to the final value of soil suction. Now, R in this case is simply going to be a ratio of the final suction to the initial suction. So we're essentially taking an arithmetic mapping, or a ratio mapping here of suction to go from the suction plane into the zero suction plane, such that our RW is going to be 1 for no wetting, 0 for full wetting. So the SPM method is somewhat unique in that it is anchored at 2 points. It's anchored at the point I in the field where we have no volume change because there is no suction change. And it is anchored at point B, which is the method B D4546 test result, or the swell potential from the lab that we obtained actually following the field stress path that we anticipate for the field. Once we have these, the sigma P value, we can calculate the partial wetting strain at any value of suction by multiplying our the log of the swell pressure divided by our surrogate final stress, and then times the slope C sub H. So very simple computation, and normally in practice we would not even look at this in 3D. I'll show you briefly what this looks like for the collapse case. I'm only looking here at the zero suction plane, but this is still the SPM method. When it comes to collapse potential, we actually have to use 2 companion specimens. One we perform by full wetting from the overburden stress, for example, A prime here, wetting fully to point B, and this is our observed collapse potential from our D4546 test. And then we, at a different stress level and with a companion specimen, we test at P prime and we wet fully to observe the collapse potential at a lower stress level. Normally, we would then connect these and project back to estimate point G prime being the estimate of the stress level that we would have to apply if we wanted no volume change when we fully wetted the specimen. So you can think of it as G prime being analogous to the swell pressure if we had an expansion response. The only difference here is that instead of using R, we have 1 minus R, of course, because we have collapse response. Okay. Let's take a look at the SPM, looking at the MSSA perspective, because it'll be helpful in kind of assessing how accurate we might expect our results to be. So we're first going to look at a case where we have an elastic response and where the soil remains in the elastic region of our state surface. So we're going to perform the ASTM method B test going from I to F to B, and that follows the field stress path, IFB. B will fall on the state surface for S equals 0. Now, IG is a constant volume swell pressure test. And so this is a constant void ratio test going from I to G. And we increase P as we go to keep the void ratio the same as it is at I. G will also fall on the state surface, and the path IFB, the path IFB will be exactly matched by the path, the surrogate path G to B. G to B falls on the actual state surface for S equals 0, and G and B are both in the elastic range, which makes this true. Now, let's take a look at what we can say if we have some elastoplastic response, because in general, when we do the D4546 test, we really don't know whether or not our observed response was elastic or elastoplastic. So here's an opportunity to look at what happens if in fact we have some elastoplastic response. So again, we're going to perform the ASTM D4546 test. I'm going to assume that in this case, our field specimen starts at point I, and it happens to fall on a yield curve. This is a reasonable assumption to make, that we're sitting on a yield curve. Now, when we run the response to wetting test, the path we're going to follow, IFB, is going to be an unloading, so it's going to follow along on this elastic plane IURS. And so we can also perform a constant volume test, I to G, holding the void ratio constant. We'll notice in this case, because we started on a yield curve, when we wetted while holding the void ratio constant, we're actually going to yield the specimen, and we're going to end up at point G on the elastoplastic surface. So our field curve, our field path lands at B. It's an elastic path, but our constant volume path is constant void ratio while wetting, and it ends up on the elastoplastic surface. So path IFB is elastic, and it is still, in spite of G being on the elastoplastic surface, GB is exactly going to match IB. But notice that now GB is slightly different than the state surface. It's not going to match it exactly because we had some elastoplastic response. It is indeed a surrogate path, and that surrogate path is not precisely the state surface when we have elastoplastic response, but it does in fact precisely give us the actual stress path IFB. So there have been some laboratory tests done where we used suction controlled odometer devices and directly measured swell strain and compared to SPM computed strain. This work was done by Singol. And you can see by looking, I'm not going to talk about everything, but you can see by comparing these last two columns that there's pretty good agreement. A similar result of good agreement between directly measured and computed strains was found by Olise and some work done by him in 2017. All right, what does it look like if we look at the MSSA for a collapse response? Well, here, we're going to start again at point I, our specimen in the field. And the stress path that we're going to follow in the field is I to T to B. So we're going to be elastic from I to T and then elastoplastic T to B. We're going to estimate that by our surrogate path or our estimated path IFB. Then we're going to take a companion specimen, one that is identical as possible as we can get it to point I, and we're going to test it at a lower stress level, say point J here. Again, using the 4-5-4-6 test, we're going to follow a path J to S to G. Now, for this hypothetical example, we're going to assume that point G landed at the void ratio corresponding to the void ratio of I in the field. So G is kind of analogous to our swell pressure, but it's actually where we can wet without getting any volume change. And that's here for these two tests. Now we have point B and we have point G, and we can thereby develop our surrogate path on the zero suction plane. And what we observe is that the actual stress path, ITB, is very closely followed by our assumed path, IFB, and therefore very closely followed by our surrogate path, which matches IFB, and that surrogate path is BQG. So BG falls on the actual state surface. Why? Because in this case, both G and B were on the elastoplastic surface, meaning our two test specimens that we had here both created an elastoplastic response when we wetted them fully to zero suction. Now, we can also use the MSSA to compare the SPM method to some other fairly common methods. So the surrogate path method, again, is somewhat unique in that the solution is anchored at point I and also anchored at point B. And remember, the actual field stress path is followed in going from I to B. So when we use the surrogate path method, the slope on the zero suction plane that we're going to use to make our computations is G to B. Now, this gives us a very accurate match to the actual field stress path. And remember, B is, we're assuming, is the field response. Now, in the Fredlin and Litton methods both, the user is allowed to select on the zero suction plane either a path GB using the ASTM method B test result and the swell pressure, or alternatively anchoring the solution to the swell pressure test result at point G, and then assuming that the unload, that is an elastic unload process when we swell, and that it is going to be along the slope here to B prime, where the slope GB prime is actually the slope of the unload wetted curve, C sub S, that one obtains from doing a consolidation and unload after the saturated swell pressure test is completed. So notice that in this case, that B prime can be, if we have elastoplastic response in our swell pressure, can be very different than point B. And this then is always going to be the case unless IB and IG are both elastic, in which case B and B prime are the same. But anytime we have elastoplastic response, B and B prime will be different. Notice that we can underestimate the swell potential if we use GB prime rather than following the path GB, which follows the stress path in the field. So the SPM avoids the potential unconservative estimate of the slope of the surrogate path And that's because it's anchored at I and B, and you can't really get a very wrong result because of that anchoring process. So factors affecting swell test results, we know, include water content, degree of saturation, density, stress path, wetting sequence, method of testing, and I would emphasize including time allowed for equilibration. And there's a very good article that's presented by Kumar et al. In 2020 that kind of summarizes these effects. It's quite possible and in fact useful to use the MSSA to evaluate, therefore, these very common odometer laboratory test results with an eye towards which laboratory test results might we glean the most meaningful results from for our practice-based application. So the ones that are really common, at least in the United States, and I know in some other parts of the world are also commonly used, that we're going to look at the ASTM D4546 test result, which is the odometer test response to full wetting for either collapse or expansion. Methods B and A, so we get the volume change potential or the multiple specimen swell pressure. And then method C is the load back. We let the specimens swell and then we load it back to get this an estimate of the swell pressure. Another test that is fairly common is the constant volume swell pressure test. And although there used to be an ASTM standard, this is not used anymore, but it's still, the constant volume swell pressure test is still used. What we're going to do is we're going to use the MSSA, but I just want to point out that in our initial look at the problem, we're going to, for simplicity, neglect hysteresis. We could include it if we wanted to, but we're going to set hysteresis aside in making these comparisons for now. Okay, first, we'll look at the method A and method B ASTM methods for swell potential, followed by method C load back. So here, what I'm going to assume is that the specimen or the element of soil as it sits in the field was at point I. Once we get an undisturbed sample, we're going to be sitting back here at point A on the 0P plane. So we start at point A, we follow a constant water content loading to point I, and we assume that we have corrected for as much sample disturbance as we can by that reloading process. I'm not going to get into the details here, but we have found that for unsaturated soils, they're not as sensitive to the sampling process, for example, as soft saturated clays. But anyway, we go from A, constant water content, come back here to the overburden stress at point I. Once we're at point I, we're going to follow the wetting path under constant P, I, F to B, and that's going to give us our swell potential. Once we have completed our swell potential test, we're now going to perform method C, which is the load back test. We're going to go from B in the zero suction plane to S, that'll be an elastic process, and then from S to G, and in this hypothetical example, that'll give us an elastoplastic response. And G then is our load back swell pressure. Now, alternatively, we could have run a constant volume swell pressure test at field overburden, going from A again to I. Once we're at I, we hold the void ratio constant. We wet, increasing load to keep the void ratio constant, and again, ending up here at point G. Now, I will point out that this path shows us that G is the same, whether we do the load back test or the constant volume swell pressure test. And I know many of you are thinking those don't always give us the same result. And that is true. My finding on this is, in my opinion to date, is that a lot of this has to do with the equilibration process and how long we're willing to wait. For example, on the constant volume swell pressure test and also on the swell potential test. And there have been some very excellent work done lately. I'm sorry I didn't include the references, but you will find them in the Kumar paper that I did reference. that shows that those 2 points begin to come together from the load back and the constant volume swell pressure test as we allow more time for the equilibration process to occur. And again, here we're neglecting any hysteresis type effects. So that is the ASTM method A, B, or C. And now we're going to take a look at another test that is allowed for in the ASTM method, but is very commonly performed, which is the the token load swell pressure test, and also the token load swell potential test. So again, our specimen is point I. We're going to start at point A, which is our undisturbed specimen in the field. Now we're going to apply a token load, a very small load, maybe 5, 10 kPa some people try to use. You have to use dead weights to hold that practically. Anyway, we're out at A, token load. We're going to wet to point R. Then we're going to load under saturated state to point B, and then to S. And then we're going to stop when we get to the void ratio corresponding to our field specimen at point A as it was unloaded when we sampled it. So that's the token load swell pressure test. Alternatively, we could have done the constant volume token swell pressure test or the unconstrained test and followed a constant void ratio path from A over to J. Now, again, notice that the load back gives us the same as the constant volume if we wait long enough, but you'll notice that J is not at the same stress level as G, and so the swell pressure at J is not the same as the swell pressure at G, and we should not expect those two to be the same in general. And then another test commonly done is the multiple specimen test. This will be the last one that we look at, but it is very commonly used, especially for compacted fills. So what we do is we perform method A if we have compacted soil, B if we have natural soils, and we do this on companion specimens. So again, let's say that we're interested at an element of soil at point I. We start at point A, which is our undisturbed specimen. Now what we're going to do is we're going to load back to point I, and then we're going to follow the field stress path I to B to get our swell potential at point B upon full wetting. So this is our swell potential once we give it, take it to zero suction at overburden stress. Then we're going to take a companion specimen as close as possible to what we had for our first test, corresponding to point A. And now what we're going to do is we're going to load it to a higher stress level, a stress level higher than we had at point I, a p-value, in fact, corresponding in this case to what I'll show here is point X. Once we reach a p-value at point X, you'll notice that what happened is in going from I to P along this constant water content path, we actually yielded the specimen. So X is on a different yield curve than I. We wet it and we actually unload here along a new elastic surface, which is below the one that we had when we unloaded at point I, and that will give us point D. Notice that the swell potential that we have at point D falls below the state surface for point I, so it's below the state surface. Once we have those two tests, what we're going to do to estimate the swell pressure is we're going to connect B to D and project downward along this slope to point M. The swell pressure is taken as point M. Point M corresponds to the magnitude of P that we would have to have at point K, such that when we wetted from K to M, that we would get no strain upon full wetting. So you can think of point M as representing the transition between the expansion potential and the collapse response, between expansion and collapse on the S = 0 plane. Well, what's important here is we've looked at several different methods to get the swell pressure. The swell pressure methods that we got, 2 of them gave us point G, 2 of them gave us point J, which is not shown, but was in this position here. And now a third method, the multiple specimen test, gives us point M, which is also not equal to G, the stress level at G, or the stress level at J. So the swell pressure at M is not equal to the swell pressure that we estimated at J, and is not equal to the swell pressure at G. Now you then might argue, well, which is the right answer? We could postulate that most of us would probably select G, but they're different. We shouldn't expect them to be the same when we do the test, following different paths and using different methods. Okay, so let's conclude what we found here. One, different unsaturated soil protocols are definitely required for volume change applications compared to fluid flow and shear strength problems. Shear strength is typically something that increases when we increase suction, and this makes it possible for us to use empirical chi-type single stress formulations for limit equilibrium practice-based problems. This is because the volume change is secondary for these limit equilibrium type analyses. And also because we can get away with assuming that the shear strength is going to increase with suction, because so often for interesting applications, it does. However, a chi-type single stress approach is not possible for volume change problems because any soil with some plasticity can expand or collapse upon wetting, depending upon the confining stress that we have at the time. And indeed, it's a very common field scenario where we can get expansion or collapse even within the same soil profile. Also, we see that the MSA provides the big picture framework for judging simplified models, tests, analyses, and protocols with regard to how well they might model the field actual stress path. And we have found that a stress path approach to unsaturated soil volume change problems ensures an appropriate model for the region of interest of our unsaturated soil elephant that we're dealing with in the field at the time. So the MSSA, if you look over here, it can help us stand back from the picture and see everything from a more holistic view, and thereby improve our judgment of the simplified processes that we're using. Thank you very much for your attention and for the time. I know it's been kind of a lengthy set of presentations, but I appreciate your patience. Thank you very much. Yes, this is true. And in fact, if you're going to consider volume change in your unsaturated flow analyses, which I might argue you should do, or if volume change is not secondary, then you certainly do need to couple, and you will have a path dependencies for sure. However, what we have found is that in many applications, we've been able to get away with using our unsaturated flow properties as if they are not volume change sensitive. Now, we might have used a volume change corrected soil water characteristic curve, and we may have done our saturated conductivity. Certainly, we should have done our saturated conductivity test at the stress levels and for the particular fabric and conditions that we have in the field. But short of that, we normally then assume when we do unsaturated flow that those things are staying relatively stable. If that's not true, for example, if you're modeling a peat soil or something like a high volume change scenario, then you can't get away with that. But in many applications, that's what we do. So that's why these protocols, these simple protocols, have been developed. Similarly with shear strength, you can find that there will be some scenarios in which you can't afford to ignore the volume change component. But when we're doing, in particular, limit equilibrium problems, then we can get away with it to a large extent. But you need to always keep your mind open that unsaturated soil response in general is always going to be relative, somewhat, complex and something that you need to be aware of in doing your simplified models. Good question. Thank you. The answer is you could, but I think for practice that this is not practical. I think when we're dealing, and I'm trying to focus on what might we do when we're dealing with practical problems. The best thing I think there is to try and obtain specimens that are going to match not only P and S, but are going to have the same structure as you have in the field. They're going to have the same composition, the same fabric, the same structure, and then observe on a macroscopic level what's going to happen. Now, in research, of course, you can do other things. You can be more complicated, but in practice, we really need to be looking at some simpler approaches and trying to just again, it's the concept of this path appropriate solution, starting with specimens that are as close as possible as you can get to your field condition, and that would be my recommendation for practice, not so much for research.